All attendees are in listen-only mode.
Hello everyone, and I hope you're having a great day. We're going to be showing a nice webinar on accurate source modeling, particularly with LEDs. I'm your moderator. This is Mike Govin. I'm the VP of Sales and Marketing for Lambda Research Corporation, and your presenter today is going to be Dave Jacobson, who's our Senior Application Engineer for Lambda. The format today is going to be a short 25 to 30-minute presentation, and I'm going to turn this over to Dave Jacobson. Thank you for attending.
Yeah. Thanks, Mike. Again, my name's Dave Jacobson, Senior Application Engineer here at Lambda Research. I'd like to thank everybody for attending our webinar session this afternoon. As Mike mentioned, our webinar is going to be it lists a 25 to 30-minute presentation, but based on this morning's session, it's going to run a little bit longer than that, but probably not by too much. At any time during the webinar, please feel free to submit any questions you may have using the question box on the GoToWebinar control panel. So just type your question in and then click send, and we'll look at all the questions at the end of the webinar. So the subject of today's webinar is accurate LED source modeling using TracePro. And the topics we're going to look at today, we're going to do an introduction to ray tracing. Now, most of the people on today's webinar session have probably been ray tracing for a long time, but just in case if we have some newcomers and for anybody who may watch this in the future, we're just going to walk through some quick basics on ray tracing. Then we'll take a look at what's required for accurate source models. We'll talk about the different types of source models in TracePro. And we'll also look at the source modeling tools in TracePro, the utilities that we have that can make the job of setting up your sources and your properties for your source models much easier. We'll discuss choosing the right source model. So what's the correct one? What's the pluses and the minuses of each different option? And then our last subject we'll show you some measured versus modeled results. I have a couple LED versions that we can look at, as well as a xenon lamp that I did some complete series of measurements on, as well as building a model of, and we can look at that as well. And then again, we'll wrap this up with a question and answer session at the end. So once again, as we're going along, please feel free to type in questions at any time. I always like to let people know that some of the additional resources we have for finding out about different topics in TracePro. The first is our past webinars. Usually on about a monthly basis, we present these webinars, and we keep archive copies of all of these webinars on our website, and they're available at the webinars section off of our main homepage. We also have tutorial videos available in the video section, as well as written tutorials where you can follow step by step and with sample models as well. And then lastly, we have TracePro training classes. Usually 3 to 4 times a year we'll hold a training class here in Littleton. But we also have the option, if you're interested in customized training, we can come out to your site and present a training course on your site for your employees. If anybody's ever interested in something like that, drop us a note. We'll be glad to discuss that with you. So a little bit of housekeeping here. The latest news is that TracePro 7.2, the newest release of TracePro, was released about a week and a half ago on July 20th. And this can be downloaded by anybody with a current maintenance and support agreement from our website, www.lambdares.com. Included in TracePro 7.2 is our new 3D interactive optimizer. Will allow you to create freeform and asymmetric shapes and optimize them, as well as our new DMD reptile option, which will allow you to create and model digital micromirror devices, DMD devices. So we encourage anybody that wants to download that, take a look at it. Our webinar from last month, the June webinar presented by Mike Govin, focused on the new features in TracePro 7.2. So you're welcome to download that from the website and take a look at some of the features that were described in that webinar. Okay, so let's get started on today's topic, modeling LEDs in TracePro. But as I mentioned, I want to back up just a hair and talk about a quick introduction to ray tracing. Again, most people probably today are familiar with this, but it's always good to have a quick review. So ray tracing is calculating the path a light ray will take through an optical system. And this can take into account absorption, reflection, transmission, scattering, fluorescence, diffraction, and a whole other range of terms as well. In many cases, you're going to have to trace a large number of rays, millions or more, to get the most accurate answer, especially if you're looking at things like uniformity and you're designing a luminaire of some type and you want to light up a desktop or a floor or a wall. You're going to need to trace a lot of rays to get a nice even illumination, see what the actual pattern is on that surface. Fortunately, programs such as TracePro can simplify this task and automate a lot of it. So here we see a very simple ray trace. We have refraction through a lens, and then we have reflection off a mirror. There's no losses, no scattering, very simple, the simplest form of a ray trace. Here's something that's a little more close to reality. We're seeing reflections back from both the front and back surfaces of the lenses, causing ghost images. We're seeing refraction, absorption at the surfaces, scatter from the mirror surfaces here. So there's actually a lot more happening in the ray trace than what that previous slide showing with just rays being focused and then reflected. So this is where programs like TracePro really come into play for modeling all of these additional effects. And basically, 5 things can happen to light when it hits a surface. It can be refracted, reflected, absorbed, forward scatter, and a backward scatter. And that happens at every surface. And that's not even bringing into account the volume effects, what's happening inside the object, things like bulk scatter. And then all of these parameters can vary as a function of temperature, wavelength, and incident angle. So there can be a lot of things happening with the rays. Then we tie this all together, we basically get an optical analysis. In this case, we're looking at a little LED spotlight shining on a target and using the true color version of the irradiance map in TracePro to get a feel for what's the color and distribution like of this light. Okay, so let's get back to the topic at hand for this month. We're going to start off looking at what are some of the requirements for making accurate models and source models. Well, the first thing is we need accurate geometry. Now we can create this right in TracePro. We could import it from a CAD program such as SolidWorks, Pro Engineer, CATIA, Inventor. I don't have it listed here, but if you're working with a lens system, you can also import lens files from Oslo, ZMAX, Code 5. Bring those in. So the more accurate you can make your geometry from the beginning, the better your results are going to be. But we also need accurate properties. Now these could be surface properties with defining absorption, reflection, transmission, scattering. Material properties where we're looking at the index of refraction and the absorption extinction coefficients. We could also add in bulk scatter, and then we're going to be defining the anisotropy, so the likely direction of scatter, as well as the scatter coefficient, which is the mean, basically related to the mean free path. How far does a ray travel before it's scattered? We can also have fluorescence properties. If we're doing white LEDs and we're modeling with phosphors. And in that case, what we'll be adding in is the excitation, the absorption, and the emission spectra, as well as things like the concentration and the quantum efficiency of the material, or of the phosphor. And the last thing we need is accurate source models. So this is how we're getting light into our model. And now we'll be looking at things like the spectrum of the source, the beam pattern, both in azimuth and polar. You know, do we have a uniform source? Do we have an asymmetric source? And then as well as the emission. How much light is the source actually putting out, either in radiometric or photometric terms? So to take a look at some of the options we have for modeling LED source models, and I'm going to focus on LEDs, but most of these techniques or most of these things are also applicable to almost any source that you're trying to model. First thing we could look at is a point source. In this case, it's all the lights coming from a single infinitesimally small point. Expanding on a point source, we could have a grid source, which is a flat two-dimensional grid of points, either annular or rectangular, but again flat in just 2 dimensions. Next would be a ray file. Now a ray file is the manufacturer or company will take their their source, LED, lamp, really almost any light source, and measure it in a goniophotmeter. What the goniophotmeter does is it scans all around the source, saves that information, and they generate what's called a ray file. And the ray file contains the XYZ starting position for each ray, as long as the XYZ direction vector and the flux. And each line on a ray file represents a single ray. So these, if you have 5 million rays, you can imagine we now have a ray file, or a file that's at least 5 million lines long. Some examples of this would be Opsera from Germany. They make their Luca ray set, which is a collection of measured LEDs. Many times from the LED manufacturers themselves, you can download ray files right from their websites. And what you want to look at there is that usually they're available in several formats, and you want to download the TracePro format. Typically the file extension will be a .ray or a .dat. And also IES and LDT files are examples of ray files. And these are typically seen in the lighting industry, where you're transferring photometric data from one program to the next. And I'll talk a little bit more about IES and LDT files shortly. Now, another way of modeling a source would be a surface source property. And this can be any surface in your model, 2 or 3 dimensional, and it'll contain the spectral and beam pattern data for that source. I should mention each one of these will go into a little bit more depth here coming up as well. And then the last would be 3D solid models. These would be creating an accurate CAD model of the LED or the source, adding in all the appropriate model properties, surface properties, material properties, fluorescence properties, and then actually letting the model itself determine what's the ray pattern, so that the geometry and the structure of the source determines what happens with the output. Okay, so let's talk one by one the different types of source models and how they can be applied. What I'm going to do here is I'm going to take this single lens here, a little TIR hybrid lens. This was actually done in our interactive optimizer as an exercise a year or 2 ago, so I use this as one of my demos. And I'm going to go through each of the different types of sources, apply them here at the correct point on this lens, and see the difference in performance we see as we change the type of source we're using in TracePro. The first thing we're going to look at is the TIR hybrid lens with a point source. So all the rays are going to be starting from a single point. What I've done is I've normalized that each source I'm ray tracing here is going to have 1 watt of output. So I can correlate between the different options to see what's happening. Here I'm looking at an irradiance map. So the distribution of light at my target some fixed different distance away. And we can see we get a nice small spot of light. And if we look down here, we have the candela plot, or an intensity plot. I left this in radiometric units, so the units for intensity in radiometric are watts per steradian. If anybody's interested in finding out more about the different types of units that are used in TracePro, radiometric and photometric, check out our radiometry and photometry website webinar on our website. But here we're looking at 440 watts per steradian. So we have a fairly tightly collimated beam, a very small point of light. Now if we change that to something that's a little closer to reality, let's say we have a 1 millimeter chip or 1 millimeter LED die, which is about what's right for this source. We can see our spot has grown considerably, and our intensity has dropped from about 440 down to 95 watts per steradian. And the beam is much wider as well if we look at this in its angular distribution. So we've gotten closer to what we'd really expect from this as opposed to modeling it just as a point source. I also went, in this case this is an Osram LED, I think it's a Golden Dragon Plus that I used here. I downloaded a ray file from the website, and I inserted the ray file into the model, used that as my source. Again, my irradiance map looks very similar. There's the grid source, the file source, and my angular distribution, my intensity, also looks very similar. We went from 95 watts per steradian down to 91 watts per steradian, so in the same ballpark with roughly the same beam shape. So we've improved upon the point source either with just a grid source or a file source. And we can also look at this with a surface source property. And what I did is I downloaded a picture of the LED. In this case, it was an IGES or a SNP file, but I didn't apply any properties to it. I just placed it here in the model as a visual representation, and I put an object here in the center that represented the die, and I applied the surface source property to that. I made a surface source property based on the data sheet, and I'll touch on the utility we use for that here shortly. Now here our irradiance map looks very similar, and our candela plot, or our intensity plot, again looks very similar to the two previous cases. We're a little bit higher, 98 watts per steradian, so I'd probably also want to look at what's the appropriate size for this surface that I applied the surface source property to. So 4 ways of modeling that and 4 different results, 3 of them fairly close. So just some examples of the data and the information that was used to create those models. Here's an example of array file data. And if we look at, say, just the first line here, we're seeing an XYZ position. That's where the ray starts. XYZ vectors, so that's the direction the ray is going. And then the flux. In this case, we've got our first ray starting at 0, 0, and it looks like 4.9 e to the 1 millimeters, and then its direction is 0, 0, 1. So this one case is going actually right down the z-axis with an included flux of about 9.14 to the minus 1. Now, one thing, as I mentioned, each line represents a ray, so these can be very long if you want to trace a large number of rays, 1 million lines, 5 million lines. Usually the manufacturers will give you the option of downloading different size ray files. Now this one here is in a text format, so we can read it. We could make changes if we wanted to. But then we can also get these in binary format. And in binary format, the advantage is the files are smaller, but typically you're not going to be able to decode them and read them or make changes to them. Now one thing is I have a line here. It says these are typically monochromatic. So this is the data for a single wavelength. And if you're looking at color, you need to either get multiple ray files or try to edit them to add different wavelengths to it. But there are some upcoming changes and upcoming updates to the ray file formats that will permit full spectral data. So they'll be able to include the spectrum as well as the angular distribution. And when these formats are finalized and released, TracePro will be able to work with those as well. So here's an example. And what I did in this case, for this LED, an Osram LW-W5AM, it's a white LED, Osram makes available two ray files, a blue and a yellow. They happen to be at 0.46 and 0.47 and 0.57 microns. And I set this model up. I inserted the ray files. I put a surface just past the source and ray traced them and recorded the results. In this case, these are true color irradiance maps, and we see a little bit of difference here between the blue and the yellow. So the blue is going to be the light leaking through from the direct light from the blue LED, and the yellow is the phosphor, the converted light. And we see here when we mix them together, we do get something close to a white LED. In this case, once I mentioned, it's 5 million rays per color, and we use 2 ray files in the TracePro model here. Now, I mentioned briefly IES and LDT files. Well, these are also ray files. And IES is the Illuminating Engineering Society of North America, and LDT is a file format most commonly used in Europe, in short for IllumDat files. And both of these are ways of transferring photometric data, so angular positions and candela values. And sometimes these are used for LEDs as well, and when I get to a couple slides further on, I'll say why these sometimes aren't always the best choice. If you have an interest in IES and LDT files, check out our October 2010 webinar. Many times you'll see you'll generate a model in TracePro, you'll save the results, an IES or an LDT file, and then transfer those to a program such as Oxytec's Lightstar 4D, where you can actually place them in a room environment and model, see how that light fixture is going to work with furniture and wall coverings and floor finishes, different things like that, so more of an architectural type modeling. And here's an example of IES data. We have our vertical angles, our horizontal angles, and then the candela data. And in this case, this candela data here is for the 0-degree horizontal angle, and then each of these vertical angles. And then there'd be the next line down would be the second horizontal angle and all of the vertical angles. And lastly here is an example of a surface source property. And we can see that the emission or the output of the source can vary as a function of temperature, wavelength, polar angle, and azimuth angle. So this can be used to fully model the spectrum and angular distribution of the source. A quick slide that I like to use on some of my demonstrations is I made a model with about 40 objects in it, and I applied a different surface source property, in this case each one from the catalog that's in TracePro, the Osram Golden Dragon LEDs. I applied that to each one of these surfaces, ran the ray trace, and looked at the results in true color. And here we can see, and hopefully it's showing up on people's screens, but the different colors, reds, blues, greens, whites, ambers that we can get from this, as well as, such as in this case here, we're seeing more of an elliptical pattern. So we're seeing asymmetric outputs. So that's a case where we use the azimuth angles in addition to the polar angles for the angular distribution. Another application I like to show, not LED related, for a surface source property is the arc of a xenon lamp that might be used in, say, a digital projection system. And then lamps like this, we have a cathode here and an anode here. And the arc of the lamp, the luminous intensity is brightest right at the tip of the cathode, and then it falls off as we move away from that tip of that cathode. And we can model this by creating a series of nested solids in TracePro and then applying different surface source properties to each one of those to model that change in luminous intensity. So the last source type here we'll talk about is actually creating a full 3D solid model of the LED. So we're going to build the LED from the ground up. What do we need to do this? What do we need to get started? Well, first thing is we need the physical information about the LED, including the die and the mount. We want to find out the optical properties, such as surface properties, material properties, and the flux, the output of the LED. Geometric shape of the components, things such as the epoxy and any secondary optics that are in there. If we're looking at a white LED, a phosphor conversion LED, we're also going to want to have specifications for the phosphor, including the excitation, absorption, emission spectra, concentrations, and quantum efficiencies. And lastly, ideally we'd want to have some experimental or measured data so we can use that to calibrate our model to make sure we've actually built a physically robust and correct model. Now here's an example that one of my colleagues did for an LED. We have the drawings of the different parts of the LED here, the die, the overall drawing of the body of the dome of the LED, as well as the structure here for the anode and cathode, and then the emission. And then here's just a picture showing the LED actually lit up and projected onto a piece of paper. Now if we take a look at how this model was actually built, if we look at some pictures here, close-ups of the die and the phosphor and the epoxy, we can see there's actually a higher concentration of the phosphor lower down in the reflector cup than there is in the upper part. And here's a profile showing, in this case here's the LED die, different parts, the epoxy fill, the reflector. And what was actually done in this is we used the 3D, the interactive optimizer, the sketch utility in the interactive optimizer. We took a bitmap image here, this picture, inserted that into the optimizer, and used that to construct the geometry of all the different parts, and then sent that over to TracePro to be used as part of the model. A little close-up of that, where we see the reflector cup, the LED dye, the fact that lower down in the cup, the phosphor, the sedimentation, has a much higher concentration than up at the top, that the phosphor tended to settle down to the bottom. Also used in this model was the TracePro, the fluorescence property generator utility. It's a feature in TracePro Expert that you can find in the utilities menu. And we can use that to set the absorption and the absorption, excitation, and emission spectra, as well as the source, in this case, say a blue LED that's illuminating this phosphor. And from this, we can get some color analysis, CIE color coordinates, CCT, correlated color temperature, or CRI, color rendering index, which is a measure of how accurate the source is compared to some standard. We can also get a prediction of the mixed color. So we have some of the blue light leaking through as well as some of the light from the phosphor. What's the resulting color going to be? And if we're aiming for a certain particular color temperature, we can also get an estimation of the thickness and the concentration of the phosphor layer that we'll need. So here's that LED model. We see a picture of it. Here it is in a silhouette view, and then a rendered view here in TracePro. Makes it a little easier to see the different components that way. So let's jump back here and let's take a look at a couple of the tools that we have available to help you set up your source models in TracePro. First is the surface source property generator utility. And this utility lets us take a beam pattern and a spectrum right from a data sheet, whether it's an LED data sheet or any lighting manufacturer data sheet, and we cut and paste those graphs for the spectrum and for the beam pattern into this utility, and we just basically click on the curve to trace that curve. The more clicks we do, the closer we can follow the curve. And then when we finish that up, we can see some of our results here, and we can actually get an estimate of the CCT, correlated color temperature, and the color rendering index. So we can get a feel for the source even before we've done anything with it. And then we can export that over to TracePro, and it'll insert that right into your surface source property catalog database in TracePro, so you can use that with any of your models in the future. I should note, if you go to our videos section off of our homepage, we do have a couple tutorials on using this utility, some step-by-step videos. I mentioned this briefly before, but we have our fluorescence generator utility, and once again, we cut and paste an emission spectrum and an excitation spectrum, define the limits of the graph, and then click to follow the curves. And if we also add in a curve for our source, in which case it's this curve right here, it's a blue LED, we can see the resulting color. And we're seeing here's the residual spectral. This is the blue light that gets through the phosphor. And then here's the phosphor emission. And combined, these two will make up the white light. So we can go up here, change the residual percentage, see what the effect is going to be, see what our resulting color temperature and CRIs are going to be. And the last utility we have in this vein is our IES and LDT import utility. If you received an IES file or an LDT file for an LED, this utility will let you import that into TracePro and use it either as a file source or as a surface source property. So another handy utility if the only information you have available is an IES or an LDT file. So let's talk about choosing the right source model. What are some of the pluses and minuses of each of these approaches? I've grouped point sources and grid sources together. They behave similarly, so we're going to just cover them here in one slide. They're best for planar sources that have planar or flat surfaces that have a well-defined boundary. For sources that emit in a Lambertian, Gaussian, or a uniform manner. And they can also be either monochromatic or polychromatic. You can set up multiple wavelengths if you want. Where I would say they're not the best would be as if you have a three-dimensional source, some source that has not just length and width, but height. You also may not be able to model some of the more complex angular distributions. But where you do see these being useful, fiber optics, and the output of laser diodes. Now the next would be the ray files. And these are the files, either you get them from a company that's doing Gaussian photometer measurements, or you download them from the manufacturer. In TracePro, ray files are called file sources. These are good for planar or three-dimensional sources, sources that can emit in a complex angular pattern, typically sources that can be modeled monochromatically, and sources that may have lenses or structural elements included. And what's nice is you don't actually have to build a 3D model. You can just insert the file source, and because it's based on measured data, all of that structure in those components are taken into account. Some of the considerations here, that typically these are defined monochromatically. Although, as I mentioned, that's starting to change, so hopefully in the near future we'll also be able to have full spectral definition in these file sources. It's not always a good choice if the emitted light will interact with the source, and I'll talk about that a little more in my next slide. And then lastly, I mentioned that IES and LDT files are forms of a ray file. The problem is IES and LDT files treat the light as a point source. They don't have any position data for the ray, so there's no XYZ position. All the rays are coming from the same point, and basically they're defined by an angle and a candela value along that angle. So some examples where you may want to use ray files, LEDs or luminaires. And here's what I was mentioning. As I mentioned, there's no structure associated with the ray files, no geometry. So to kind of demonstrate the point here, I inserted the CAD model of this LED along with the ray file. And some of the rays here that are emitted from this file source are TIR, totally internally reflected by the lens, and they actually hit back on the source. And I used the ray sorting features in TracePro to actually show the rays here that are hitting this surface of the LED. And in this case, about 0.1% of the initial flux is impinging back on the source. Now that may not be a problem, but in other applications it may be a problem. The value may be higher. So you may, if you're worried about things like that, you may want to move beyond file sources and get into actually physically modeling the source, the LED. Now, surface source properties, great for detailed source models, sources that emit in complex angular spectral distribution patterns, and where you may want to start to look at modeling the interaction of light with the source. Some of the considerations, as you would expect, the models can be more complex to make, and you're going to need accurate material and surface properties. Some examples here: LEDs, different types of lamps, arc lamps, filament lamps, as well as complete systems. If you want to start modeling complete optomechanical systems, you're probably going to start to lean towards surface source properties. Here's an example of an LED surface source property, a little desk lamp here. In this case, I'm using, once again, true color and then the new 3D irradiance map feature in TracePro. And I can see the light hitting my tabletop as well as light that's hitting the body of the lamp itself. So another way here, we're getting our full color capabilities along with the angular distribution. Now for the 3D solid model, it's pretty much the same requirements there that it would be for the surface source property. We're going to want to use this when we're doing detailed source models. Again, sources that emit in complex angular and spectral distributions, and where modeling the interaction of light is important. And once again, the same issues crop up here. The models can be more complex to make, and we're going to need accurate material and surface properties. And then once again, LEDs, lamps, and complete systems. So a lot of times a solid, a 3D solid model will have the geometry, but it will also then will have a surface source property in there as well to act as the source. Here's an example, once again, that short arc lamp might be used in a digital projector. We have a dichroic filter here, so we have one wavelength being passed by the filter, another wavelength being reflected. So we're able to fully model the spectrum of the arc and get different spectral behaviors based on that, on the wavelength. Okay, so for the last topic here we have before we get to our question and answers. And once again, I'll remind everybody, feel free to submit any questions you have using that question box in the GoToWebinar control panel. We're going to look at some measured versus modeled results. Now, first thing I want to look at is that LED we previously showed. Here's the picture, the silhouette version, and the rendered view of that same model. And what we've looked at here is we've taken a picture shining the LED on a piece of graph paper, or grid paper. And we can notice here a couple things. We have our white light spot here in the center, but around that we have this spot, a ring of yellow. And what that is that's light basically just from the phosphor. That's not necessarily getting the blue light from the LED chip illuminating it. So this is kind of a glow around there. And if we come back here into TracePro, this was taken at a 10 centimeter distance from the LED to the target. Setting up that model with that same distance, looking in true color. Here's our white square, pretty much mimicking what we see here. And then here's our yellow ring, a little bit of glow around that. So we're able to actually get to model the same phenomena we're seeing when we actually light up the LED and project an image of it. Here's the angular distribution. Placing the LED next to a surface, we can see the light and we can see what its angular distribution looks like. And again, how it matches with the candela plot, both a polar and a rectangular candela plot in TracePro. So again, good agreement with what we're actually seeing for real results. Now a second LED, and this one varies a little bit from that first one. Basically, it's the shape of this dome. This one's a little rounder, squatter. This one's a little more elongated and taller. So we'd expect to see some different results. Once again, here we are. We're a little bit closer, 2.2 centimeters. White spot with a fairly large area, glow area around it. And similar to what we're seeing here in TracePro. Once again, true color radiance map at the same distance. Our candela plot looks quite different. We have a much broader source compared to here. Here's the candela plot for both the polar and the rectangular versions. So by changing that lens shape, we've changed the angular performance of the LED by quite a bit. The last example, this is something I used to work with quite a bit in my past, so I'm very familiar with it, but this is a pulsed short arc flash lamp made by Perkin-Elmer, who's now Excelitas, a company I worked for a long time. And I took this lamp and fully measured it, did a full angular distribution of it as well as a spectrum, and I built the model in TracePro as well. Some of the features, we have a window, we have a body made out of Kovar or stainless steel, we have tungsten electrodes, we have an arc formed between these two electrodes, as well as this here, what's called a trigger probe that initiates the arc and guides the arc. One thing to note too is you may see in the bottom here is white. I'll show how that affects it in a few slides here. And the other thing is I took a picture of the arc. I did this with a CCD camera, and we can see the arc is actually brightest in the center, and then it falls off as you move away from it. So here's the arc I created in TracePro. It's really just a series of nested cylinders, and I varied the luminous intensity on each one of those as they moved out, based on the values I got from this picture. And here's my measured versus modeled results. And what I did to get these results, scan back up here, is I rotated around this lamp. And one direction of rotation was this way, across the electrodes, and the other one was this way, along the length of the electrodes. So we'd see different angular distributions because of the positions of the electrodes. And one thing I was happy to see is on this side here, both the measured is the blue data, the brownish data with the square is my model data. And I saw a dip on this side, and that dip is caused by that trigger probe sticking into the arc, and it's blocking a small amount of light. The other thing I noticed is that this distribution here across the top, we would sort of expect it to be flat, flat angular distribution, but we actually have a little bit of a peak here, and that's due to the white base of the lamp. It's actually reflecting some additional light up, and it's causing it to go more into the center section, being apertured by the front of the lamp. So we get a little bit of reinforcement right in the center. And again, our modeled results agree very well with our measured results. Also goes for the spectrum. I took a spectrum of this lamp and used that to create a surface source property for the arc. In this case, my measured data was at a finer sampling interval, 0.7 nanometers. When I ran the ray tracing TracePro, I just did a 2 nanometer sampling interval. But again, we can see most of the structure still holds true. So a good agreement from one to the other. So to sum up what we've looked at today, we've looked at several ways to model a light source. We showed some examples of the different types of sources and how they perform with a constant lens. We talked about how the best option really is going to depend on the application. And we also looked at surface source properties and 3D models as being the most versatile. They give you the most capability to change and add things. We also talked about how the accurate source models are really going to depend on accurate property definitions. If you don't have good property definitions, you're just taking really a shot in the dark. And then we showed some good correlation between measured and model data for both LEDs and, in this case, a xenon short arc lamp. So with that, I'm going to wrap up my presentation. I'm going to have Mike come back on, and we're going to start take a look at any questions. And I see we have at least one question, so I'd encourage everybody or anybody that has a question, please feel free to submit it using the question box in your GoToWebinar control panel. I should note that we will be putting an archived copy of either this session or a morning session on our website either this afternoon or tomorrow. So if you want to go back, rewatch the webinar or download the slides, that should be available within 24 hours in the webinar section of our website. So let's go on to questions and answers. Mike, are you there?
Well, Dave, thank you very much for that excellent webinar.
Thank you.
And I am opening up the question portion of the webinar here. We have a question: is there a drawback to combining a lens's angular output and the LED's power and color distribution into a single surface source property applied on the distal surface of a physical replication of the lens?
That would be a good way to do it. The only thing I would caution is if you would, really where it comes down to, if you were using, say, data from the data sheet to create your angular distribution for the LED, and that had a lens on the front of it, and then you were applying that data to the lens as well, you can in effect be double applying the property. But if you're taking an LED as a bare chip, putting a lens on it, running it through that, then making a surface source property based on your measured data, yeah, you can then do that. But in that case, I'd be applying it to a flat surface because you've already taken the curvature of the lens into account when you've run the original ray trace. Hopefully that.
We have a second question here on that same type of information. Because LED flux is related to input current, is there a way to change the flux of a new surface source without creating a new surface source property?
Yes. Let me just go open up TracePro here. Should have had it open from the start, but.
If anyone else has any questions, please feel free to type them into the question section of the webinar, the GoToWebinar panel.
So I'm going to take this surface of this block. I'm just using a sample block and apply a surface property to it. And now I've been using Osram all day, so let's do KARI. Okay. You'll notice here we have a scale box, and you can use that scale box or that scale value to scale the output of this source up or down without actually having to change the property. So if we wanted twice the output, we just type in a scale value of 2. If you want half the output, 0.5 for a scale value. So you can make changes very quickly without actually having to go in and edit the property. And if we do this, if I actually apply this property, an even quicker way of doing that is going up to Define and then the Surface Source Editor. And that'll show you all of the surfaces, all of the surface sources in your model. And you notice one of the columns here that we can edit is the emissivity scale. I could select that column, say 2, scale, and it'll scale the emissivity that way. So very easy to change. This surface source editor window is great when you have a large number of sources in your model and you don't have to actually go through the model tree and select them one at a time. I believe we included this on the Tips Tricks webinar that we did a couple months back. So there's some more info available there as well. Okay.
If we have another question, we use a lot of Sol LEDs, and I'm finding that most of their published data on their website, Ray Data, DIS, or TXT, are not compatible with TracePro. We are considering purchasing ProSource. Is this the best resource for production LED Ray data?
I would say if they're making the files available in the ProSource format, that's probably the only way that you'd be able to get it. But I'd also try checking with them. If they have ProSource, they may be able to supply it to you, because ProSource outputs TracePro Ray files. It's one of the options. So they may just not have included it for some reason, but maybe if you touch base with their applications engineers, they can supply that to you. But if you do have the raw ProSource files, then by using the ProSource software, you'd be able to get those, be able to get the TracePro format files from that.
We also have a webinar that is on the website that you can actually go through, and it talks completely about the Ray files that we use and what the formats are. Our Ray file data, there are 2 formats. There's an ASCII format and a binary format. The ASCII format shows a 7-row header that specifies that it's a Ray file, and the other, after the first 7, it actually has row after row of Ray data, which is only 7 bits of information. That's your XYZ position, your XYZ direction vector, and the flux associated with that ray. So if you're opening up one of these Ray files, you should be easily able to tell if it's really a valid Ray file or not, that we can read it or not. Of course, in the binary-wise, you do have that problem. You can't read the file. But usually with normal DAT or TXT files, you can read those files and ascertain if they're correct or not. And sometimes just changing the header will make those files available to be used.
Okay, well, that's a good point. So there is, if you can find a sample or use the slides in here that show that the TracePro Ray file format, if you have to modify that header, you can go right ahead and do that and see if that'll work.
Dave, we have another question here. Can you walk through an example of applying a manufacturer's Ray file
Sure.
in like a step-by-step type manner?
Sure. Okay, I'm going to go back to TracePro and delete that model. Open a new one. And I'm going to go to Define and File Source. And the first thing we want to do is give it a name. I'm just going to call it, in this case, LED. And then I'm going to click here to browse for my source file. And I am going to go, I already have some Ray files downloaded. I know I have some good ones from Osram, so I'll use the one that was in the webinar, the W5AM. I'm just going to change my file type to all types. And these are our Ray files that I downloaded from, in this case, the Osram website. And we can see here we have a Ray file. We have 6 different ones. We have blue in 5,000,000, 100,000, and 500,000 rays, and yellow in 5,000,000, 100,000, 500,000 rays. So for convenience sake, I'm just going to pick blue, 100,000, click Open, and TracePro reads that file in. Now it's going to insert it at basically where the manufacturer defined that. And typically they're right around 000. We could offset it from that if we want, but for this case I'm going to insert it here at 000 with the default rotation. In this case you can see they've also specified a wavelength, 0.46 microns. This is a binary Ray file, so I can't go in and change that wavelength or modify it. And I'm going to click Insert. Now you notice it doesn't insert any geometry. And if I come over to Source, if I click on that here, I can see I now have LED under my file source. And it inserts, TracePro inserts this little wireframe sphere to kind of roughly bound where the rays are starting from. So you can get a bit of a visual representation of where that source is. And if I run my ray trace just as I normally would run a ray trace, there's the output of that LED. No geometry needed. So very easy to insert these and then add them to your ray traces. And these sources can be moved, rotated, copied as well. So you can have, you're not limited to just one. You can make a copy of this if you're doing an array of LEDs.
I think also if you want to verify that that source is correct, you might want to do a polar isocandela plot, which will also tell you how much flux is coming out of the LED, and you can also verify what the angular output is actually the same. So that's actually a good check to I always perform on whenever I bring a ray file in.
Yep, I'm just going to change it to make sure it's a photometric here. Run that ray trace just to double check it. And if I go to Analysis, Candela Plots, Polar ISO Candela, I'm going to change my analysis units to photometric. We're seeing we can look at the lumens value and the angular distribution, in this case of this source. So a very good way to, normally I'll do, as Mike said, is I'll run this type of array trace, and then I'll use the scale factor to adjust it to meet the values on the data sheet.
You have one final question here, Dave. Many of the Cree LEDs we're modeling have an advertised flux tolerance of plus or minus 7% on the LED data sheets. Are there methods to add this unknown into simulations?
What I would do is, I guess a couple ways. You could probably write a little scheme macro that would change that, change the scale factor, and run through, say, 3 different ray traces, nominal, plus 7%, minus 7%. Or you could make 3 separate surface source properties and change them, or just go through and change that flux value. Do 3 different ray traces. Do one at a scale of 1, the other at 0.97, the other at 1.07, and then compare the results that way. Just save them as separate files. But that's really you need to, the easiest way to do that is to just change that scale factor and rerun the ray trace, which at times can take a little bit of time, but it certainly would be worth it if you want to see the effects of the variation in the tolerances.
I think that's all the questions we have. I want to thank everybody for attending the webinar. If you would like to see this webinar or re-watch it again, it will be on the website in the webinar section. Thank you all for attending, and I think we're going to wrap up the webinar at this point.
Okay. Again, thanks everybody for attending.